Now, let us see the third case. What happens when the speed of the object or the flow is more than the speed of sound? That is, we are dealing with the situation when this happens, then it means the Mach number is greater than 1. In this condition, what happens that since the object, that is the source in our case, is moving at supersonic speed, therefore, at various time instants, the spherical front looking like a circle in 2D case is something like this. Whereas, suppose at the current location, the source is here, whereas it has given the at various earlier time instants, let us say 1t, 2, 1, 2, 3, in those cases minus 1, minus 2, minus 3 earlier time instants, it has emitted the spherical wavefront like this. Now, in the supersonic case, this source is considered as apex, and downstream side the earlier planar wavefront becomes a conical shape. This cone is again called as a Mach cone in 3D case, and 2D representation is that two straight lines here, that is at some angle here. The half angle which this Mach cone, let us say the upper one, makes with the center line along which this source is moving is known as Mach angle. And let us say at t equal to minus 3, if from where the spherical source was present here and it has immediately emitted this front which is moving at t equal to minus 3 seconds, then if I draw a perpendicular on this Mach cone, please observe that this Mach cone is basically tangent to all these circular fronts shown here. Now, from this center, if I draw a perpendicular here, somewhere here, then the Mach angle, using your basic trigonometry, I can write that this is the object, this length is traveled by the source, that is our object, in 3t and multiplied by the velocity, assume v. Therefore, this distance becomes 3vt, whereas this front from moving from here with the acoustic speed, this front at t equal to 3 seconds will be 3at. Using the basic trigonometry, that is the hypotenuse divided by your perpendicular, gives you the Mach angle represented here, mu, gives you sine inverse of 1 by m. Now, all this flow pattern, that is the pressure pattern which we have discussed, is basically evolved by the von Karman's rules of supersonic flow. There are basically three supersonic front rules, that is the von Karman's has given, proposed. They are the rules of forbidden signal. It says that the pressure changes produced by a body moving with a speed faster than the speed of sound can never reach upstream. That is, whatever the information produced by the object will be localized in the periphery of the object itself, and it will not reach further upstream. And that is why we evolved the zone of action and zone of silence, which is present over here, that inside the Mach cone a zone of action is here, that all the information produced will be localized to here, whereas outside will become zone of silence, where no information in the flow field is passed, that is the information of movement of this source or object which is here. Second rule which von Karman proposed is nothing but zone of action and zone of silence. As I just said, that zone of action is the information zone where the happenings in the flow field is known, whereas the outside boundary, that is the Mach cone, outside the Mach cone information is not passed. Furthermore, the third rule of von Karman is nothing but the rule of concentrated actions. That means all these spherical wave front that is circular in 2D case shows their proximity is basically the pressure disturbance intensity. That is, intensity of pressure disturbance is in the proximity of this. By seeing the pattern, you can observe that what is happening inside this. In supersonic flows, the rule of concentrated actions takes place. That means all these flows which we have seen the flow pattern here, the pressure pattern here just now, this is in this flow situation, supersonic flow, where the object is moving more than the speed of sound, the zone of concentrated actions takes place, predominates. And the very beautiful application of this, that since childhood days, whenever we are in the under the open sky, and whenever there is a jet aircraft is flying, we used to see that even though in a clear sky, when the weather is clear, if we can spot the supersonic plane, the fighter planes, then after some time only we hear the sound produced by it. By the time the aircraft might have passed or covered several distance from you. Why it happens that you observe, you notice this, the movement of flying of this fighter jet, only that the mic cone, this tip is affecting your ears. Till then, you will not be having, even if you could spot the fighter jet, you will not be aware of the sound produced by it. However, as soon as this tip falls on your ear, then you will hear a huge noise, and sometimes if it is flying at lower altitude or just took off from the nearest air base, then you will try to close down your ears. By covering your ears, you avoid the huge noise produced by this fighter jet. So please keep in mind that the zone of concentrated action of Karman's rule applies over here. Now, let us see that we keep talking about that various flow regimes, about fluid mechanics, fluid dynamics. In our case, since the fluid is air, aerodynamics, gas dynamics, rarefied gas dynamics. This classification can also be done with the help of non-dimensional number, that is non-dimensional speed, that is nothing but the Mach number. And we essentially see here that what happens when the Mach number is less than 1, what is called this zone, when the Mach number is equal to 1 and Mach number greater than 1 and Mach number 1 more greater than 5. And we define this as subsonic. This is called sonic speed, or this is supersonic speed, and this is termed as hypersonic speed. Using this exercise, which is popularly termed as adiabatic flow ellipse in the gas dynamics, we are going to derive that equation, and we will see what parameter that is which defines the Mach number, that is ratio of speed of the object to the speed of sound, which of these parameters affects, which covers and segregates in these regimes in different domains with the different nomenclature. Let us again look at the steady one-dimensional non-adiabatic, that is non-conducting energy equation is given by H naught H plus V square by 2, applicable for steady and non-conducting. That means, let me write down the applicability of this equation: steady, adiabatic and non-conducting. Inviscid. Please look at these. the steady case, we have just said that the local derivative of the time with the property variation with respect to time is 0. Whereas adiabatic is this, that the flow domain is not occurring, it is insulated and it is not having any heat exchange with its surrounding. Whereas please look at the non-conducting. The non-conducting means within the flow domain the heat transfer is not taking place. That means the temperature gradients are not such that the heat is flowing from one place to another place under the analysis. Second is the flow is inviscid, that is the viscosity effect, viscous effects are ignoring. One must be careful about the adiabatic and non-conducting. Adiabatic is case that the flow domain is insulated, that the boundary of the system is insulated, whereas non-conducting, the internal flow is not exchanging the heat from one part to another part. That means there is no source of heat or sink of heat is also present. Under these many conditions, the H naught is equal to H plus V square by 2 is utilized. Now here we will go. Suppose this equation is applied for a perfect gas. We have seen that dH is equal to Cp dt, and from the speed of sound relation we can write down A square is equal to gamma RT, or T is equal to A square divided by gamma R. Using these, if we apply this in our energy equation, what we are getting is something like this. That means you can note down here that H naught we have, or you can say here that is H naught is becomes Cp T naught, whereas H is equal to Cp T plus V square by 2. Now Cp is given as gamma R upon gamma minus 1. If you replace this thing, then it becomes, then this becomes Cpt, that is gamma R T naught divided by gamma minus 1 is equal to gamma R T divided by gamma minus 1 plus V square by 2. And since gamma RT0, I can denote, let us say, a stagnation speed of sound A square by gamma minus 1 is equal to A square divided by gamma minus 1 plus V square by 2, and that is what exactly is written over here. This speed, which is A square upon gamma minus 1, is also termed as the maximum speed. Please note that this side, this equation equal to this is nothing but a elliptical equation. To ensure this, since this side, if this is a constant value at the particular speed, stagnation speed, then we can say that is at the stagnation temperature which is not changing for the flow medium, because it is adiabatic case, then this equation, if we divide this, then this becomes equal to 1, and this is nothing but a elliptical equation. Now first quadrant of that elliptical equation is drawn over here. Between, this is the equation between the speed of sound A and V. So on this axis, at the y axis, along the y axis, I am taking the A, along the x axis I am taking V, and this is something V maximum, which is obtained here when the temperature is 0, that is T equal to 0, a theoretical case. Now if we draw, then based on Mach number we can divide here at various dotted line, we can show this ellipse in the first quadrant. This line segregates and further as well between various flow regimes. When this line is drawn at Mach 0.3, in which please recall in our discussion we have said it that Mach 0.3 is the Mach number in aerospace sciences, that segregates between incompressible flow to the compressible flow. Now, below point 3, this is the completely low speed incompressible flow, whereas as soon as the Mach numbers moves ahead, this is a compressible flow. However, still this is less than 1, then it is called subsonic. The second line which segregates is drawn at Mach number 1. In this case, we see that the Mach number 1, which is also called sonic flow situation, and this is a boundary that the incompressible flow completely, that is the subsonic flow, incompressible subsonic flow, compressible subsonic flow, and then it moves to supersonic compressible flow only. Now, from here to this place, that is drawn another line at Mach 5, and then this domain is called hypersonic flow. Now, we are going to analyze by seeing this diagram what happens in these zones. That means likewise here, and similarly let us say here. If we try to see again the phenomena that is we are interested in the speed of the object to the speed of sound, or the flow speed with the speed of sound, whatever relative, then in this subsonic incompressible flow, since the flow speed small v is very less than the speed of sound. Further, by seeing this graph, please see that in comparison to the speed change, the flow speed change, the speed of sound variation, change in the speed of sound is very small. That means the Mach number in this zone is predominantly affected by velocity alone and not with the changes in the speed of sound. Whereas, when we move to subsonic, that is beyond 0.3 but less than 0.1, in this zone still the velocity is still less than a, that is the speed of sound. However, by looking at this graph, note that the Mach number from this zone to this zone, still I cannot say that change in velocity is much higher than change in speed of sound, though it is higher. However, I can only make a comment that the Mach number from 0.3 to 1 is predominantly changed by change in speed, but secondarily by speed of sound. Whereas, if I move from 1 to less than 5, that is the hypersonic limit. In this zone, again the V is greater than A. That means the change in speed and change in A, by looking at this graph, are of comparable magnitude, and in this domain the both change in speed and change in A are basically affecting the flow situation, and equally we cannot say that this is primarily and this is secondarily. However, as soon as we have drawn a limit as m equal to 5, we say that the predominantly change in Mach number in this domain, flow domain, is only secondarily through speed while primarily to A, and since the speed of sound depends upon temperature, we can in turn say that in the hypersonic domain, hypersonic flow region, the temperature has a predominant factor in changing the Mach number, and that is why in all hypersonic applications in aerospace sciences give a prominent due consideration to the temperature or heat transfer effects while designing the spacecrafts. Now, going ahead with this background, what we can say here, I would like to make two more comments before moving ahead. Please see that though we have segregated between 0.3, 1, 5, that is subsonic, supersonic, hypersonic, there is a transition zone also exists which we call transonic region. Transonic region of flow or transonic flows is something about approximately 0.75 to Mach number existing with lesser than something about 1.2. What we notice that it means if it is starting somewhere here and it is up to here, this domain is termed as transonic flow region. What we observe here that this some portion 0.75 to 1 lies in subsonic region, while 1 to 1.2 obviously it lies in supersonic region. But the transonic flow is a region or a branch of compressible flow which is studied not together with normal compressible flow subject, but it has its own due to its own characteristics, it is studied separately. Why it happens? From our flight mechanics background, what we understand, as soon as the subsonic, high subsonic flow approaches or the Mach number achieved by the aircraft in the standard atmosphere comes around 0.75 or something in that range, or maybe 0.6, 0.64 sometimes, depending upon the, let us say, the airfoil or wing used by the plane and the speed. What happens in this region, as soon as the flow is something, let us say tentatively and around 0.75 or 0.7, the flow over the, though the upcoming stream is subsonic, the flow over the wings is behaving something abrupt shock wave, which we know that a lambda shock wave formation takes place above the wing. That means even the upcoming stream is subsonic, the flow over the for some reason, for some length over the wing becomes suddenly supersonic. That is, a transonic flow situation is mixed situation, that is has both subsonic and transonic, that is supersonic flow situation. That is why it is studied separately. And when this happens, we say that this is a critical Mach number we have achieved. And as soon as we go beyond this critical Mach number towards 1, we find the drag experienced by these planes are tremendously rising, and then we say the drag divergence Mach numbers comes into the picture, which suddenly increases the drag where the lambda shock formation by the lambda shock bifurcates and ecological losses occurs over the wing, which is of course compensated by the propulsion, the aircraft propulsion. That is why the transonic flow requires a separate study altogether because of its abrupt behavior. Furthermore, we should also see that what is the quality associated, that we have defined the hypersonic plane, hypersonic flow exactly at 5. Why not 4.99, 4.98, 4.97 and not 5.01, 5.02? Please see that the discussion we have just seen it, that in these increasing the Mach number, that the speed, the Mach number changes is primarily affected by, dominated by the change in speed of sound and secondarily with the speed of the flow. This, due to the nature, exactly happens, and people have experienced on the several occasions past many years, that it exactly happens at Mach 5, and that is why it is a worldwide accepted limit, lower limit of Mach number 5. Moreover, I would like to mention over here one more fact about the hypersonic flow, since we are introducing the subject, which you must appreciate. Please listen that lower limit of the Mach number, we have said just that Mach number 5, due to this consideration, that is the speed of sound consideration and in turn the temperature consideration, the Mach number 5 begins the hypersonic plane. But what can we say that beyond, let us say, Mach 100, is a hypersonic flow situation? What about Mach 60? What about Mach 200? If we can achieve, at least theoretically we can discuss. Please note that whatever the analysis we are performing and we are claiming about the flow situation macroscopically, considering the flow phenomena as a continuous media, that is still the continuum hypothesis holds, but something around the Mach number as soon as reaches around 38 to 42 on an average, the Mach number approximately equal to Mach 40 energy equation which we have derived TD inviscid non-conducting flow situation is H plus V square by 2. Using this as a perfect gas, assuming the perfect gas till this Mach number, we find the temperature is the order of around 10,000 Kelvin. In this temperature range, till this assumptions of a continuous media, that is the continuum hypothesis holding, is true. Beyond this temperature range, as we said, the nitrogen completely dissociates, because we have seen the perfect gas discussion that around 9,000 with the perfect gas assumption, which is a approximately true assumption, because when we take the dissociation effect of these molecules into account, then something around 9,200 Kelvin, the perfect gas assumptions does not hold. In that situation, the gas is completely dissociated at very high temperature, and this state we know that this is a plasma state. Therefore, theoretically the hypersonic limit, that is the hypersonic flow situation, is the upper boundary is also present, and then tentatively we can say that the Mach number greater than 5 but below Mach 40 is my hypersonic domain. Please keep in mind. Now we move to our discussion towards an important term known as compressibility factor. Why it is important? When the flow situation is incompressible, we perform some analysis. When the same flow, let's say if it is compressible, then also we perform the analysis using the whatever discussion about the governing law, conservation laws. Now, idea is, suppose any compressible flow medium where the flow is happening and you are interested in analyzing, but you consider for your convenience this flow to be incompressible, and then you analyze the situation. The task remains that assuming a compressible flow to be incompressible and analyzing the situation, how much error you are incorporating in your estimation, and that factor is known as compressibility factor. Let's say first situation is that when an incompressible flow is brought to rest isentropically. We know from incompressible Bernoulli equations from the aerodynamics point of view or fluid dynamics point of view, P naught is P, let's say static, plus half rho V square, neglecting any height change, that is without incorporating the energy, potential energy term. And for our purposes, aerospace application, the potential energy term is ignored. Therefore, the Bernoulli equation takes the form of P naught equal to Ps plus half rho V square. This P naught minus Ps, that becomes half rho V square, is termed as incompressible dynamic pressure, that is represented as Q incompressible, that is the dynamic pressure experienced by the flow in an incompressible flow situation. Here P naught is rather than a stagnation, we more precisely say this is a total pressure, which we have seen from our fluid mechanics background. Now, if this situation is considered to be compressible, then what happens when a compressible flow which is having where the motion is happening and you brought down this compressible flow isentropically to the rest, that is reversibly and adiabatically. Then whatever the property, as we said in our discussion, thermal properties, the thermodynamic properties, that is pressure, temperature, density, all becomes with a subscript 0, and we said these are stagnation properties, that is those thermodynamic properties where the flow speed 0. However, this flow speed has been achieved from a moving fluid to the rest isentropically. Under this situation, from the isentropic relation which we have already derived, we have seen that P naught by P can be written as 1 plus gamma minus 1 by 2 m square to the power of gamma upon gamma minus 1. Now, considering the same fact of dynamic pressure, let us see if we calculate P naught and we are interested again for a compressible flow P naught minus Ps. Then what I will do, that I will subtract minus 1 both sides in this equation. That will lead to me is something like this expression, that is, let us denote, since this is a compressible flow situation, and then we can make Q with the subscript comp, which essentially represents compressible flow. Now, since P naught minus Ps is Q compressible, then I can write down Ps in the big bracket 1 plus gamma minus 1 by 2 m square to the power gamma upon gamma minus 1 minus 1. From mathematics background, we know that this is something which is of the form from a binomial expression, something 1 plus x by n. Using the series of this binomial expansion, if we open that series, we find something like this. And then one some term I have taken deliberately in common, and then it leads to me static pressure which was already present here, then taking some factor common in this expression, and then it goes to 1 plus m square upon 4 plus m to the power 4 upon 40 and so on. Now, my task is Q incompressible I have already calculated, which is here half rho V square, whereas I am getting the compressible flow situation is some compressible flow equation something like this. Now, if I divide the compressible flow dynamic pressure and incompressible flow dynamic pressure, then this Ps gamma m square by 2 divided by, and this break bracket term divided by half rho V square I must investigate. Now, please note that half rho V square, which is true for incompressible dynamic case, let us convert in terms of the Mach number, which is more dominant parameter for a compressible flow situation, how it comes. Now, in this scenario, let us see that half rho V square can be converted in terms of the Mach number, such as 1 by 2. Using the equation of state, I can directly write static pressure P by RT, and since we are conventionally using static pressure with subscript S, let us I put S here. Now, and then multiplied by V square is already present. In this case, now if I solve this again further, then let us algebraically manipulate, that is, let me multiply gamma at the denominator as well as in the numerator, and then further V square is there. Clearly, you will observe that 1 by 2 gamma Ps remains, and this fellow becomes a squared, which is nothing but a speed of sound square, and then V square is already present. This two term will lead to you the Mach number square. Therefore, what I will lead to is 1 by 2 gamma PS m square. Now clearly see that in this expression of Q compressible and Q incompressible, I am already having gamma PS m by 2 m square. That means the below term, this term can be replaced with gamma PS m square by 2, which will cancel the numerator term. Then we will lead to the final term something like this. Now, by definition, the compressibility factor is defined as the Q compressible by Q incompressible minus 1, that is, take this fellow this side. In doing so, Q compressible minus Q incompressible divided by Q incompressible is termed as compressibility factor. Let us represent it as in the abbreviation C dot F dot, which I have represented here for you. This gives you m square by 4 plus m to the power 4 by 40, and you can consider as low as Mach 0.4 or let us say 0.6, and you will be surprised to see the error incorporated in such an analysis is more than 25 to 30%. Therefore, a compressible flow situation can never be assumed for the designing purposes as incompressible. This have a check given by compressibility factor, which you are always going to calculate using this expression. Please keep in mind. Now, what we are going to say here something like a theorem. We say that an adiabatic non-conducting flow equation here is always isentropic. To prove this, that if I say that this is true by this inviscid case, that I am having this assumption as well, that this is inviscid, this can be proved right away. That is, an adiabatic non-conducting flow steady and state energy equation given by this is in turn brings you inviscid assumptions as well. Now, please see that H naught is equal to H plus V square by 2 can be differentiated to bring something like this. If you take a derivative both sides, then dH naught becomes dH plus V dV. Let us say this is equation 1. From combining the first and second law of thermodynamics, Maxwell has obtained this equation, which we have already seen while discussing the thermodynamics. TdS is equal to dH minus VdP. For the time being, assume this is equation number 2. Now, going further, this dH minus VdP essentially here gives me a specific volume, and since this specific volume is given as 1 by rho, in this case replace that. That's what I have done here. dH minus dP by rho is equal to TdS. Now, furthermore, one more equation, that is the nothing but Euler equation. If I take, then what I feel that dP by rho plus V dV is equal to 0, and since this is true for all situations, therefore the integrand itself can be considered as 0. Now, by considering this, let us say this is equation number 3. Now, I am going to solve these equations 1, 2 and 3. First, my task is, let us remove some terms. For doing so, I am going to subtract the equation number 1 and 3, that is dH plus V dV, dH plus V dV is equal to 0, and then in this equation left hand side I am going to subtract minus dV dV 0. That means this, if I am subtracting, this essentially becomes something like this. However, this V dV will be cancelling out, and then we will remain dH minus dP by rho is equal to 0. Now, since this dH minus dP by rho we have obtained from equation number 1 and 3, this is going to be 0. Let us insert this value here. What immediately we will lead that TdS becomes immediately 0 since temperature is not 0. Therefore, the choice left is that ds equal to 0. That means if you integrate, you can say the change in entropy is 0. That means the entropy is essentially constant for this process where you are applying steady non-conducting adiabatic flow energy equation. That means any steady adiabatic non-conducting flow is also isentropic, and that is why this energy equation we are applying based on these 4 conditions. Please remember this fact. Now, let us move ahead something more important to the compressible flow, and I can say a basis for our various equipments used such as generation of thrust. This is the basis, please understand carefully. This is an important relation in compressible flow is termed as area velocity relation. To derive this relation, we commonly consider in a fluid flow situation where the flying is taking place or a supersonic flow or a compressible flow even is taking place. In that situation, let us consider a stream tube. A stream tube is a hypothetical tube which is surrounded by a bunch of streamlines under steady phenomena such that the local change of the properties with respect to time is 0. However, you are not zeroing the spatial distribution, that is the spatial gradient of the properties are still possible. That means that the area is still changing under the steady case. In doing so, this exercise, please note if the flow which is taking place inside this stream tube surrounded by the streamlines here, bunch of streamline, and hence it is called stream tube. Due to the property of streamlines, no flow can move in this direction. That means when the streamline surrounds a flow, a cross flow situation does not occur, because if this is allowed, then at that particular point, if we allow the flow to cross the streamline, which is a violation of the principle or definition of the streamline, that any cross section, any intersection point of the streamline, the velocity directions will be 2 or multiple. In that case, suppose if 2 streamlines cannot intersect, we say, because as the intersection point there will be 2 tangent can be drawn on respective streamlines. That means at the same point 2 velocity directions of the flow is impossible, and that is why the flow can never cross a streamline. That means this streamlines which is surrounding the flow forming the stream tube is acting like a solid surface. With that statement concept in mind, we will move that let us this stream tube is of the length something like dx, and the variation of the area, spatial variation of the area is we are allowing. That means let us say if the variation coordinate is x, therefore let the area is being varied from this place to this place with respect to x. Now, from continuity equation, rho AV is equal to constant, which is nothing but again m dot whatever the flow is incoming is only coming out, and since the mass is not allowed on the surface, then whatever mass is entering is essentially coming out. Therefore, m dot is constant for this stream tube, which is considered a hypothetical surface, a tube in a flow domain. where we are interested seeing the area variation and its effect on the velocity. Let us move ahead. Doing so, rho AV is equal to constant, where rho is the flow density, A is the variation of the area, and V is the velocity. Now, taking the logarithmic at both sides, log both sides and then differentiate. It leads to, when we do it, then ln rho AV will give you ln rho ln A plus ln V. When you differentiate this, it will lead to you this form. Let us say this equation is 1, d rho by rho, dA by A, dV by V equal to 0. Please look at carefully, we are going to derive a very important relation for compressible flow or gas dynamics. Now, second equation which we are considering is nothing but the Euler equation. Euler equation is the one of the form for inviscid flow momentum equation. Continuity result is VR width, and then second result dP by rho is equal to minus V dV. Now, considering the first equation dP by rho, and I am trying to utilize the momentum equation. How can we do that? Since this is dP by rho and here the first term is d rho by rho. Therefore, we have to algebraically manipulate the equation number 1. In doing so, let us bring down dP and rho. However, since we have inserted dP, then d rho by dP in the denominator as well, and then further dA by A plus dV by V is equal to 0 is automatically present. Now, since dP by rho is minus V dV, we can insert here minus dV dV V dV into dP by d rho by dP plus dA by A plus dV by V is equal to 0. Now, further, if we do this exercise here, what we essentially get that we can club these two terms dV by V with this dV by V dV, and then we will lead to that. Let us say at one side we will keep dA by A, however, all the other two terms we are sending this side. Now, when we substitute, as we said just now, that V dV and bringing to right side, we will obtain this equation. That means all the positive negative term, this will become positive that side, and this fellow which is positive will become negative, and keeping dA by A at the left hand side. Now, if we keep here, then what we see here that V dV, we can take the V dV common, and in doing so V dV common, suppose if I am taking the V dV common, dV will come out here V dV at the outside of the bracket, then we are left with d rho by dP minus, and then we can see here V dV we are taking common, then it leads to something around 1 minus V square. Furthermore, V dV V square, and then what we essentially take, let us say minus V dV if we taking common, then this become 1 minus V square minus d rho by dP, and then taking further common d rho by dP by d rho as in the numerator, and then V square in the numerator and dP by d rho in the denominator, and minus 1. Now, at this juncture, let us see one more fact here, and here this fellow will become dV by V, not the V dV. This is wrongly written here. Now, correction is dV by V and then V square dP by d rho. Now, since the process, let us say in the flow in the stream tube is happening with the changing area reversibly, and since no heat transfer is allowed from this stream tube, therefore, an adiabatic assumption is also inserted. Doing so, this dP by d rho, we can say that this is happening isentropically. The process is taking place from here to here coming out, the flow entering and flow exiting is basically isentropically happening. Therefore, this term becomes A square, and thus dA by A will be dV by V, and then this is nothing but m square minus 1. That means the final expression which we are leading with, dA by A is equal to m square minus 1 dB by V. This relationship is termed as area velocity relationship. Now, look at the characteristics of this equation. If the area, suppose if the flow is subsonic, that is the first case what we investigate, when the inlet flow is subsonic, that is m is less than 1. In this case, since suppose if dV by V is positive, that is you are interested in a positive dV by V, that is you are increasing the speed, then what happens, since m is less than 1, then dA by A and dV by V is essentially having different sign. For a positive dV by V, dA by A is negative. That means if the incoming flow is subsonic and you are diverging the passage, that is incoming flow is subsonic, while second consideration is that incoming flow is still subsonic, whereas you are converging the passage. In this scenario where dA by A is positive, however subsonic flow is incoming, therefore dV by V and dA by A is having opposite sign. That means to increase the speed you must converge the flow, and this kind of structure or duct is known as nozzle. Whereas when the incoming flow is subsonic and you are increasing the area, the flow speed, the speed will decrease. In this case, this is called diffuser. This essentially gives the definition of the passage. While in the second case, when m is greater than 1, then both dA by A and dV by V are having the same sign. That is unlike the subsonic case, since dA by A behavior and the change in velocity, fractional change in velocity's behavior is same, therefore to accelerate the flow, area should increase, whereas to decelerate the flow, the area should decrease. That means in supersonic case, this was a subsonic case nozzle and this is diffuser, while in supersonic case when m is greater than 1, then if you want to increase the further Mach number, then you need to divert the passage, and this passage here in this case is termed as nozzle. Whereas when this flow speed, that is the incoming Mach number, is supersonic, however you are interested in decelerating the flow, that is at the lower Mach number, then you need to converge the area, because you are interested in decelerating the flow, so decrease the area, accelerating the flow, increase the area, and this is called diffuser in supersonic case. Therefore, this gives a definition of nozzle and diffusers such that any passage which accelerates the flow is always called nozzle. Need not be, it should be converging, because we have just seen it depends upon the inlet Mach number. Whereas any passage which reduces the speed is called diffuser. In subsonic case it is diverging, while in supersonic case it is converging, and this additionally give the definition of diffuser as well. Now further, if we say one more point here, that in the subsonic case, please note that if the subsonic case which is coming m less than 1, at the exit of the nozzle, the maximum Mach number achieved is 1, because dA by A equal to m square minus 1 dV by V. since this is a derivative, first derivative. Therefore, what could be the maximum Mach number achieved in a converging nozzle case? Then if you put it is equal to 0, then you can see that since dV by V is a non-zero term, then for that reason m equal to 1. Therefore, the maximum Mach number achieved in a converging nozzle case is always 1. Therefore, if you want to achieve a supersonic flow outside the exit, that is at the exit you are interested in obtaining a supersonic flow, so you can clearly observe that soon after termination, that is the exit of a converging nozzle, I must diverge the passage, so that for subsonic case this becomes nozzle, for supersonic case this becomes nozzle, and hence this is called, to obtain the flow at the exit of this duct, called convergent divergent nozzle, to obtain supersonic flow at the exit. Here we should understand this point as well, that since we are considering the straight boundary which you can observe schematically which is drawn, in this case straight convergent divergent boundary will give you the, when the flow is entering something like this, then the flow which is assumed that it is attached to the boundary, internal boundary of the divergent section and not separating, will give you the flow at the exit in different direction. They are uniform but in different direction, that is they are not in unidirectional, and this kind of nozzle is termed as convergent divergent nozzle. However, in the practical application of jets, aircraft jets and spacecraft jet in sensible atmosphere, these flows should be having unidirectional as well as uniform, so that you need not have a thrust vectoring, that is nozzle gimballing, required to maintain the trajectory, straight trajectory of the flight. And for that you contour the nozzle, that is the boundary itself is properly contoured, and that is used from one of the concepts which we will discuss in one of the talk very later, is termed as theory of or method of characteristics. If for the two-dimensional flows, where computationally we contour the nozzle, and that based on this design we form the nozzle for practical application. And to obtain, the idea is behind to obtain a unidirectional and uniform flow, so that thrust vectoring can be avoided for jets application. Thank you.